Newton's method is pretty interesting. Everything we're doing in mathematics is trying to find a solution. What exactly is our solution? When we say solution, what are we talking about? What exactly does the word solution refer to in mathematics? And actually, there are four other words that it refers to.
Value satisfies.
Philosophically, yes. No. When we say a solution, we're actually solving for the x-intercept. The x-intercepts are actually the x values that make the function equal 0. Those intercepts are also called the roots of the polynomial. And they come from the factors. So all these words pretty much mean the same thing. If you ask to find the factors of the roots, you're actually looking for the same thing. Are all functions? First off, we know that you can't factor all of them. We just had one. So we had to use the quadratic formula. Or we use the complete the square method. If it's quadratic. If it's not, then we have to go through the whole thing we learned in algebra, the Descartes rule of signs, the using synthetic division, all sort of stuff, the difference rule, the difference quotient, but I forgot the name of it, but it's where you have some function and you take the constant term divided by the leading coefficient and look for all factors of that. Remember that from algebra? So that's one way of doing it. Here's another way. It's a lot easier, a lot faster. It's called Newton. It's called the Newton-Raphson. I spell his name, Raphson. But Raphson wasn't much a contributor in this one. So we just call it Newton's method. This is a way that in calculus where we use to approximate solutions. To approximate solutions by using the tangent line to the curve at various x values. The beautiful thing about this is you only have one thing to do, is decide on the initial x value. Here's in a nutshell, let me tell you how it works. You have a function. I want to know what the solution is there. If it's something like this, well, if it crosses the x-axis, we can use what theorem to prove that one exists? The intermediate value theorem. Remember what that told us? No. It said, if we have a function and if we plug in two values in our domain, and one side is positive and one side's negative, then between A and B, there has to be a C between there where f of C is equal to 0. Now, it doesn't just have to be the x value. It could be, if it's a horizontal line, say y equals 1. As long as it's a horizontal line, I can set that as my new horizontal asymptote. And say, or my axis, I should say. And we can set that to be crossed. So what happens here is this, is I will take a value. My initial value is x sub 0. That's my only choice. And again, my x sub 0 is between those two values. Between the A and B, it's in a domain. Now, from that point, at that value, if I draw a tangent line to that curve, it crosses the x-axis at this point. I call that one x1. Now, at x1, I plug that back in the equation, and I find the point on the graph there. I find that tangent line where it crosses the x-axis. Notice every time I do that, the x-intercept is getting closer and closer and closer to the answer. That's how the Newton's method works. By taking the tangent line where it crosses the x-axis, that's your next value, x, where you begin. And this is called an iterative method. Because we begin with one value, plug it in the equation, and see what happens. Then we start with that next value and go from there. What time are we supposed to get out of here?
12:50.
I'm so sorry, everybody. It's almost 12:30. Oh no. I'm sorry. I'm sorry.
Well,
You have me scared there for a second.
yeah.
Yeah, this is called an iterative method. Because I can keep on talking forever. My evening class, I have one, and the students are so into it that we keep on talking. We're supposed to get out at 8. We're past 9 o'clock one night.
That's true.
No, it's always happens if the students want to learn, or if they're asleep already. So these are the iterative methods. Let's see where it begins. Because it deals with the tangent line. Remember how we get the tangent line? Find the first derivative, and that tells us the slope of the tangent line. So let's look at remember that equation from algebra? This is called the point slope formula. Because it has a point, x1, y1, and it has a slope. Think of what we're doing here. In this method, I pick a value, x sub 0, that finds a point. From that point, I got to take the tangent line. The tangent is a slope. So I have a point, I have a slope because the tangent is a slope. So let's solve for y. We get y is equal to y1 plus m x minus x1. So far so good? Well, we know that m is the same thing as y prime 1. So far so good? So when our entire approximation is we're trying to find the x-intercept. The x-intercept has the location x comma 0. So set y equal to 0. Let's solve for x. Set y equal to 0. Solve for x. What's the first thing I move? Yeah, you move this one, minus y1. So I have minus y1 is equal to y1 prime, x minus x1. What's the next thing I move? Very good. So I'm gonna write that. So x minus x1 is equal to negative y1 over y1 prime. We're solving for x, so we get rid of the x1. How? Add x1 to both sides. And there's our formula, actually. Oh, no, no, no. This is our formula. This x value is the goal of our entire observation. We're trying to get that x value. So here's the general formula for it. X sub n. Instead of writing y sub 1, this is f of x at x sub n, and then the derivative at x sub n. Now, the reason this is iterative, because you begin x sub n. What really this ends up with, this is x sub n plus 1. You start off with an x sub n, plug it in there, whatever that gets, that's your next value. You plug that in the value in the next equation. Work it out, whatever that is, that goes in the next value. I'll show you in long form how it works. So, but this is the only formula you need to know. Where x sub n begins at 0 and goes on until you solve it. How do you know you solve it? When your values don't change anymore.
Similar to the limit.
Yeah, it just stays the same, right? Yes. Yeah, you can say that if you want to. It goes to a limit where the values stop changing. Then it's right there. Let's look at an example here. F of x equals x squared minus 2. And it says approximate the solution. Remember our formula. Now, To help us, we can do a little legwork in front by using the intermediate value theorem. If we can find two x values, one of them gives you a positive answer, one of them gives you a negative answer, then we know where it has to be between. Other than that, if you use a computer, let it run. I mean, just pick a value, plug it in there, and it'll solve itself no matter what. But the further you are from it, it'll take you more iterations to get there. In graduate school, we let these run for thousands and thousands, hundreds of thousands of times, sometimes overnight. So x sub zero. Well, let's pick a couple values. If we pick x sub zero, what do we get? So it's 0 squared minus 2 gives us negative 3. If x is 1, 1 squared minus 2, it's 1 minus 2 is negative 1. If x is 2, 2 squared minus 2, 4 minus 2 is 2. So here we have it. Our domain that we're looking at is between 1 and 2. Between 1 and 2, there has to be an x-intercept. Follow that? Check one. So our first thing, let's pick x sub 0. Let's pick 1.5. So that's our initial x value. Here are my x values. My first x, this is at 0, x sub 0. It is 1.5. We need to know the function itself, f of x, that's x squared minus 2. So in this first one, I put 1.5 inside there. And work it out. I'll set these up and I'll do an Excel in a second. We also need to know the derivative. So the first derivative is 2x. Follow me so far? Now we got to put it all together into the formula. So we have x sub n minus f x sub n f prime x sub n. So it's 1.5 minus so let's see, it's x squared minus 2. So it's 1.5. So that equals 0.25. So the top number is 0.25. The bottom number is 3. Two times the initial value. Now I got to do this whole calculation here. So it's the initial value minus open parenthesis 2.5 or 0.5 divided by 3. 1.416667. Now, this number here, since we're only doing one decimal place, let's make it 1.41. So this value here begins my next iteration, 1.4. So now I go in here, I put 1.4 here, put 1.4 here. And we go on further. So I take that value. So what is 1.4 squared? Minus 2. So that becomes negative 0.538. At the first derivative. 2 times that's 2.8. So this one is 1.4 minus. So the function x squared, so 1.4 squared. One point four squared minus 2. So it's 0.0069.
How are you getting the, for 1.4, I multiplied 1.4 times 1.4 minus 2, and I got 0.04. Well, maybe stop doing that somehow. 1.4 times 1.4 is 2.96, right? Minus 2, or 1.96 times 2 is 0.004.
Excel stupid. So I typed in there, I put parentheses around the 1.4 and then squared it and then subtracted 2. It didn't take it that order. But no, what I got in this one now, I got negative 0.04. Wow, that's pretty strange how that does that. Okay, so this will give me. (1.4) minus open parenthesis. Divided by 28. I got 1.4 again. Know what you're at? Once you get the same thing, you're done. That's your zero. Because if you did it again, you get, I mean, because the next one, this one comes down here. And then you repeat the process. So that's why it's iteration. You start with one number and you keep on going.
One way to. Keep out of this, how many significant.
Yes, and that is what is so difficult about this. Because with Excel, let's say, okay, I'm a first, these are my X's, X of N, this is F of X sub N. This is F prime X sub N, and this is the overall X value. So the first one I put was 1.5. The formula for this one was X squared minus 2. And this was the first derivative, which was 2x. So it's 2 times. And this is where I put everything together. So I took this value minus this value divided by this value. And that one goes there. So let me see, I just copy this over. Yeah, so you see, we got this one, it came over here. That value came there, we got that, and then it stayed the same from there. So at that, this is my x-intercept right here. The point where it starts getting the same after that, this is my x-intercept right there. Because all of my x values give me the same value. Another way you can do it is if you subtract your x values.
How do you insert the prime symbol into Excel?
The what?
The prime symbol into Excel. Yeah.
You work it out yourself, and I entered that formula right there.
Okay. So
Derivative.
you just do it apostrophe, but it's not a.
Right. This is just a symbol of show me what these headings are about. Yeah, and you have to work out by hand.
Okay, yeah, you just plug it in.
Right, there is, yeah, unfortunately.
So then for this is like a question on like the theorem, is that big E, whenever you write the theorem, so like every number in subset, what is that big E? What is it? Is it a Greek symbol?
No, the big E, this here, it shows it's an exponential function. This is 4.51 times 10 to the negative 12.
Oh, you.
No, like whenever when you talk about like, for example, like every time you mention a theorem, like, or every.
Oh.
Like if I wanted to search for that symbol.
We have these two. There exists and for every.
So what symbol is that? That's not an epsilon.
No, it's a backwards E. It's just,
Oh, is it
it's a
backwards?
shorthand symbol they use for mathematics. It's a mathematics symbol. It's for shorthand. Yeah, it says for every X in the domain of AB, there exists a Y such that X squared works.
Okay, so then the E.
This is contained in or is an element of.
But is that another made up math symbol or is that a Greek symbol?
It's a set symbol. When you deal with modal logic, it's a set symbol. It deals with how sets are arranged or what's contained in one. So that is, if you look at,
Is that,
yes, let's start off with that.
so what is it though? When I'm writing it, I just copy what you're writing, but like, is it?
It just says that.
Or it's just a big E. Roman E?
This one?
Yeah.
It's because in logic, that symbol means contained in of that. It's just a symbol. This is because it can be equal to. Sets. But yeah, so that's all Newton's method is all about. I strongly encourage you, if you're not strong with Excel, try to practice, because doing this on calculators, it's the longer, harder equations, it'll get really painful. But that's all it is it's iterative, because you plug in one, plug it into the function, find the first derivative, put in the equation, whatever that equals, plug it again until it starts repeating itself. I don't think the homework assignments, any of them may go more than 5 or 6. Use Excel. If you can't use it, by all means. I would strongly encourage it. All right, thanks. I start with the mess ups, and I thank you all for a great day. See you all.
This is another.
No, it sounds. Did I give you all? Oh, speaking of, did I give you all chapter 5 note set yet? I only have 2 of them here, I think. Check on the bottom. Is that it? Yeah. That's
But
it.
you'll print it for the next class then.
Yeah, I'll print some more.
Okay.
Yes. Does anybody want chapter 5 packet printed out? Sure, because I can print it out next time. No, it's algebra.
Oh, sorry.
Different one.
That's algebra.
Sorry.
I'll bring it next time.
Okay, my mistake.
No, it was my mistake. I was supposed to get it done, but I was too busy answering